So the first sample problem we're going to look at is when we have heat applied to a test tube, right? Now, when you apply a test tube or heat to a test tube, oftentimes the bottom of the test tube heats up a little bit more quickly than the top. This gets you something known as a temperature gradient, or a change in temperature over a change in distance. And so what you're told here is that we've created a constant temperature gradient by applying heat to the test tube, which is 10 Kelvin per centimeter. Now, for the system, we're informed what the thermal conductivity is. What we've been asked, given that we have a cylindrical test tube here with a known radius, is what thermal power are we going to get? Now, when we're dealing with linear style heat transfer, like when you heat the bottom of a reagent in a test tube, we're looking at H here, where H is the power delivered per unit area, per unit time, to whatever we're dealing with here. Now, when you're using this, you have a plethora, like an absolutely insane number of options that you have when dealing with this. The reason why H here is bolded is because it is a vector. Heat can transfer in a particular direction. The question is, how do we parse this? Well, you want to look at what you're actually asked to find here. So here you're simply asked for the amount of thermal power. First of all, thermal power is a scalar, so we're going to ignore all the signs that are present in these equations because we don't care about the direction. But we need to know what power is. Power, when we're looking at power, is the change in thermal energy, so delta Q divided by delta T. That's a terrible Q. There we go. Now, if you take a look at this relationship here, what we're actually looking for our power is this term here altogether. So we're definitely going to want to use this part of our equation. Right, so we'll just underline it. Now, other things that we've been provided with the thermal conductivity. We know what it is, so that's kT, so we're going to use one of these two. And you can use the calculus one if you like, but it's probably just easier to use this relationship here. So here, even though we have this quantity h defined, we're not really caring about what it is. So this is going to be the characteristic equation that we're going to work with. Now, when dealing with this, again, we do not care about the direction because we're asked for the power. Right? So we can get rid of all the signs because signs only control direction. And here we have a characteristic equation that we're going to use to find the power P, keeping in mind that this dq, or delta Q by delta T, is the energy rate transfer that we're looking for. So what we can do here is we can rearrange this. So we're going to keep the power on the left-hand side here. We're going to move the area to the other side. kT is going to stay where it is. And here we have the change in temperature with respect to the change in distance over which that occurs. So here we have a delta T divided by a delta X. Now, our goal here is to see how much of this we can fill in. Now, when you're dealing with this, our goal is to find P, so we should be able to have all these things. We're going to start with the area. Whenever you're dealing with this, these areas are always cross-sectional. So for our area, we need to know that we have a cylinder. The cross-sectional area for a cylinder is a circle. So here we're going to have pi r squared. And we can do this because we actually have the radius, right? The radius that we have is 1 centimeter. We don't need to do any unit conversions here because every time that we've been told a distance, it's been in centimeters. So there's nothing to worry about here. So what you can do is you can take pi and you can multiply it by r squared. So if you do this, you'll get 3.14 centimeters squared. So that's the area that we need. As for the coefficient of thermal conductivity, kT, we have this. We know it's 0.5 joules per second centimeters Kelvin. And these seconds per centimeters Kelvin are all together in brackets here. And so that's two of the things that we need. The last thing that we need here is delta T divided by delta X. Now, here, you don't actually need to have delta T specifically. You're actually provided with delta T over delta X directly. If you take a look at this last number that you've been given, you'll notice it's temperature Kelvin per centimeter. The units of this are telling you that this is literally the temperature gradient that you need. Oftentimes, when you're dealing with these types of problems, you might be given more than one variable at a time. So here our temperature gradient is 10 Kelvin per centimeter. That means to find our power, all we need to do is we just need to put these together. So if you take these three things and you just flat out multiply them together, you'll get a power of 15.8 joules per second. All the centimeters and kelvins will cancel out, which is 15.8 watts. Right, so using this relationship, you can cherry pick or pick specifically just two of the parts of the relationship that you want. If nobody asks you for a direction, get rid of all the signs, and then you just need to parse what you're given in the problem in order to solve it.